Hello everyone, today we'll talk about the problem count subarrays with fixed bounds. We are given an integer array, two numbers, and we have to count all the subarrays of this array such that the minimum value in that subarray is equal to min k, one of our given numbers, and the maximum value is exactly equal to max k, the other given number. Now, while this problem is classified as hard, and it might be hard if you're not used to problems like this, if you've been doing previous dailies, you of course already know what we're going to do here. We're going to do a sliding window. The only question is what we're trying to maintain, so what we're checking in each iteration. And in this case, there's also a small twist in that it's not quite as obvious how to update the result. Okay, so let's think about what we need to track in order to be able to update our result. I'll give you two, let's say, hints or ideas, and perhaps those two ideas might be enough for you to solve this problem yourself, if you haven't done so already. So, the first idea, which is quite obvious, is that we'll have to track somehow positions of min k and max k in our array. Because it's important to know these positions, because all of our good subarrays have to include some occurrence of min k or max k. And the second one, which may be a little bit less obvious, is to track positions of bad numbers. Now, what do I mean by bad numbers? Well, notice that any number that is greater than max k or smaller than min k will poison every subarray that it's a part of. So when we see a number like this, we know we cannot, under any circumstances, include it in any good subarray. So now you may want to think about how to solve this problem by using those two ideas. And now we'll talk about an example approach. What we want to remember is last positions, both of the first type and the second type, because we don't need all of them, only need the last one. And now the only problem right now is how we update the result. So here's what we're going to do. I and j will be our typical pointers, but now I will of course be on the left, but this will be the last position of a bad number. And j will just go to the right and consider all the other numbers. And of course we'll also be remembering all the positions of the first type. And now if we know that, then we can update the result after each step. But now the result is not the typical j minus I plus 1, but it is something something, considering these positions of min k max k, minus I plus 1. And the reason for it is that if we try to add all the subarrays that end at j, then we'll be adding some short subarrays, and those short subarrays perhaps do not have the minimum value or maximum value that are equal to what we need. And this is why we have those positions of type 1. Because now the minimum of pos let's say pos max k and pos min k is a good right bound for our subarrays. And now we can start from that right bound, which is to the left of j. Perhaps it is equal to j, but it is to the left of j certainly. And anything that is shorter than that but doesn't go past position I, which is our last position of a bad number, is a correct subarray, and we can add it to our result. And this is literally all you need to do to solve this problem. Let's see the code. Notice that the code is quite short because really the solution is quite simple. You will remember the result, which has to be long, and positions of min k and max k. You see a next number, and now this here is a check if this number is bad. If this number is bad, we have to push our left hand forward, because we cannot include this number v in any good subarray. Otherwise, we'll take j minus I plus 1, but this j that we're taking is not the current j, but this j prime. And as we said, this j prime is the minimum of the last position of min k and last position of max k. And of course, if min k or max k are actually the value that we see right now, then their best rightmost position is the current position j. And after that we can return the result, and that's it.